Have you ever looked at a subway map and tried to figure out the actual layout of a city? Those brightly colored lines are great for telling you how to get from point A to point B, but they stretch and distort the physical truth to make the routes easy to read. On that stylized map, two stations might look like they are miles apart, sitting at completely opposite ends of a long, winding train line and separated by dozens of stops. But if you climbed out of the underground tunnels and walked above ground, you might find those two distant stations are actually sitting right across the street from each other. Truly understanding how a city is built requires two different views. You need the transit map to see the official, unbroken routes, and you need the geographic map to see the actual physical proximity. When scientists try to design new medicines, they run into this exact mapping problem, just on a microscopic scale. They have to figure out how atoms are arranged in a complex molecule. To do this, scientists use a nuclear magnetic resonance spectrometer, or NMR. It relies on a giant, supercooled magnet to reveal atoms' hidden positions. This graph shows a standard one-dimensional NMR scan. For a complex molecule, the data becomes a dense forest of overlapping spikes. It tells us which atoms are present in the sample, but it struggles to show exactly how they connect to one another. That one-dimensional scan is essentially just a list of subway stations. To build a three-dimensional model of a drug, we need a way to map the specific tracks running between those atomic stations. Two-dimensional NMR solves this by spreading overlapping signals across two independent axes. The first major mapping tool on this grid is COSY. It tracks specific magnetic signals that happen when atoms are directly wired together by chemical bonds, the physical links. It maps out the unbroken backbone of the molecule. This gives chemists their official transit map, showing the exact sequential order of stops along the chemical line. But while COSY provides a blueprint of how the molecule is chained together, it doesn't show what the molecule looks like in the real physical world. Large molecules, like proteins, are not rigid, straight lines. They bend, twist, and crumple up into highly specific three-dimensional shapes. To figure out that physical shape, scientists bring in a second tool called NOESY. It functions as the geographic street map of the folded molecule. Instead of following chemical bonds, NOESY detects magnetic interactions traveling through physical space, jumping directly across gaps between atoms. The signal intensity drops rapidly over distance, meaning it only works if atoms sit extremely close together, just a few atomic widths apart. NOESY is the tool that proves two atoms are physically touching each other across the street, even if you have to ride 15 stops on the COSY subway line to get from one to the other. NOESY maps the invisible architecture of the fold, showing how a flat chemical chain actually occupies three-dimensional space. In the final step, chemists combine the through bond network from COSY with the through space network from NOESY. By locking down both sets of connections, they can determine the molecule's exact configuration. Mapping these complex, tightly packed geometries is a primary tool for understanding how proteins fold and how to design life-saving pharmaceutical drugs. A drug's physical 3D shape is exactly what determines whether it can settle into a specific pocket on a disease target to stop it from causing harm. The 3D models of complex molecules we see today are the result of scientists tracing both the subway tracks and the city streets of the atomic world.